Today, we're pulling back the curtain on one of the most critical yet pretty much invisible parts of your computer, the Linux kernel's cryptography engine. You can think of it as this silent, sleepless security guard, standing watch at the very heart of your system.
So let's just jump right in with a really basic question. What's the one thing that the kernel, the absolute core of your operating system, is really truly built to defend against?
And the answer? Well, it's actually pretty simple. Untrusted code. At its most fundamental level, the kernel's main job is to create and maintain a chain of trust, making sure that whatever's running on your machine is exactly what's supposed to be there.
To really get how it pulls this off, we've got to pop the hood. Go inside and understand why doing all this heavy lifting inside the kernel is such a big deal in the first place. So why bury this deep inside the kernel? It's all about one word: performance. When a normal application needs to do something secure, it has to keep asking the kernel for permission, passing data back and forth. That's called context switching. It's kind of like an office worker who has to constantly run down to a separate, secure vault for every single file. Yeah, it's secure, but it's also incredibly slow. By doing the crypto work directly in kernel mode, you basically cut out the middleman. You get fewer data copies, you get direct access to any special hardware, and everything just runs so much faster.
And this right here is the star of our show, the Crypto API. It was introduced way back in kernel version 2.5, and it basically acts like a standardized switchboard. It lets different parts of the kernel, say the networking stack or the disk encryption system, request these security services without having to reinvent the wheel every single time. It's the foundation for, well, pretty much everything we're about to talk about.
Now, this powerful API lets the kernel focus on its number one job. And, it might not be what you think. It's not really about encrypting all your cat pictures. It's about something way more fundamental: verifying trust.
This quote is the absolute key to understanding the kernel's entire mindset. It isn't trying to be this massive encryption machine for all your data. No, its main focus, its obsession really, is guaranteeing the integrity and trustworthiness of the system itself. It's constantly asking, is this piece of code the real deal? Has anyone messed with it?
So how does it do that? Well, think of it like a digital wax seal check from the old days. When the system wants to load some new code, like a driver for your graphics card, the kernel doesn't just say, "Sure, come on in." No way. First, it carefully inspects the digital signature on that code, checking it against a key it already trusts. If that seal is authentic and unbroken, great, access is granted. But if it's been tampered with, even a tiny bit, access denied. It's simple, but it's an incredibly powerful security model.
You can almost imagine the kernel having this internal conversation. When a new piece of code shows up, it pulls out its trust toolkit and starts an interrogation. The verify signature function asks, "Okay, are you legit? Prove it." Then describe chimes in, "Who even are you? And what are you supposed to do?" And sometimes, if needed, eds follows up with, "So, can you do any other security work for me?" It's all about establishing that chain of trust before letting anything have power over the system.
Okay, so now that we get why the kernel is so obsessed with trust, let's take a look at where you can actually see these powerful security mechanisms at work in the real world. And this trust checking is happening everywhere. The most obvious example is kernel module assigning. That's our digital wax seal. But the kernel also uses its crypto engine to guarantee your files haven't been secretly altered, using tools like IMA and EVM. It helps build the secure network connections for things like TLS and IPsec that protect you when you're browsing the web. It even manages the keys for your encrypted hard drive. See, this isn't some obscure niche feature. It's a foundational security layer for the whole system. What's really crucial here is that the kernel isn't just stuck using one single method. It has what's called cryptographic agility. For signing code, sure, it supports the old guard, RSA, the reliable, established veteran. But it also fully embraces the modern challenger, ECDSA, which gives you the exact same level of security, but with smaller signatures and faster checks. Having these kinds of options is what allows the kernel to adapt and stay secure as new threats emerge. And this whole idea of adaptation brings us right to our final section.
Let's look at how these principles are shaping what's next for kernel-level security, where the future is all about being fast and lean.
And honestly, there is no better case study for this than the modern VPN WireGuard. It was built from the ground up with a single philosophy: be faster, simpler, and leaner than the older, clunky VPNs it was meant to replace. And it does this by leveraging the power of modern crypto right inside the kernel.
So just how lean are we talking? Fewer than 4,000 lines of code. Now, to put that in perspective, some other VPN solutions have hundreds of thousands of lines. This incredibly small size isn't just about being neat. It is a massive security feature. A smaller code base means a smaller attack surface, far fewer places for bugs to hide, and it's something security experts can actually read and audit in an afternoon.
WireGuard pulls off this amazing simplicity by being very opinionated. It doesn't try to support every algorithm under the sun. Instead, it deliberately chose a very small set of what are considered the best, fastest, and most modern cryptographic tools available, like Curve 25519 for key exchange. This is the evolution of kernel crypto in action, choosing a few excellent, high-performance tools over a giant, sprawling collection of mediocre ones.
So what's the big takeaway here? The kernel's crypto engine isn't just one single thing. It's this sophisticated, layered, and constantly evolving architecture. It's that unseen security guard, and its main job is to verify trust. And the best part? It's getting faster, leaner, and smarter all the time.
And that really just leaves us with one final thought. We've seen this evolution, right? From RSA to the more efficient ECDSA to the incredibly lean design of WireGuard. As our digital world gets more and more complex and threats keep evolving, what do you think the next generation of this unseen guard is going to look like? What will it need to be?